The primary decision an artificial intelligence engineer makes is determining how a system will learn from data, a choice that dictates the entire architecture of a business solution. This choice centers on the distinction between supervised and unsupervised learning. In a professional context, this is the difference between training a system using historical records with known outcomes and allowing a system to discover hidden structures within data that has no predefined labels. To understand the stakes, consider that supervised learning functions like a student preparing for an exam with an answer key. If a student is given 1,000 practice questions where the correct answers are provided, they study the relationship between the question and the result. Over time, the student learns the logic required to predict the correct answer for a new question they have never seen before. This is the essence of supervised learning. The AI is trained on data where the ground truth or correct label is already established. Conversely, unsupervised learning is comparable to a new employee tasked with sorting a mailroom containing 10,000 unsorted letters without any instructions or category labels. No one defined these categories for the employee. They identified the patterns and structures independently. In the world of data, this means the AI finds a hidden organization in datasets that lack any explicit labels. These two styles represent the with a teacher and on your own approaches to machine intelligence. While supervised learning focuses on prediction based on past examples, unsupervised learning focuses on discovery and description. By the end of this exploration, the distinction between these two paths will become the foundational framework you use to evaluate any data science project. Understanding these concepts allows a professional to determine whether they are looking for a specific answer to a question, or if they are looking for the right questions to ask their data in the first place. Supervised learning is categorized into two primary functional types: regression and classification. In a classification task, the AI predicts the discrete category, such as whether an incoming email is spam or not spam, or if an image contains a cat or a dog. When the target output is a continuous numerical value, we use regression. For instance, predicting the exact market price of a house or tomorrow's closing stock price requires a regression model. In both instances, you provide the AI with input data, known as features, and the correct label. The system learns the rule. When I see this specific set of inputs, the answer is that specific label. Referring to the visual illustration for supervised learning provided in the material, we see a training phase where photos of cats and dogs are paired with their respective labels. Because the AI has seen many labeled examples, when it is presented with a new photo of a cat, it can successfully assign the correct label. Unsupervised learning operates differently, primarily through clustering and dimensionality reduction. Clustering involves grouping similar items together, such as segmenting a database of customers based on their unique shopping habits. Dimensionality reduction is the process of simplifying complex data, such as compressing 100 different data variables into 2 or 3 primary components for easier visualization. In the visual illustration for unsupervised learning, the data begins as a collection of various shapes, circles, dots, and triangles, with no labels attached. The AI examines the features of these shapes and independently organizes them into 3 distinct groups. It has not named these groups. It has simply identified that the items within each group share more similarities with each other than with items in other groups. Between these two poles lies semi-supervised learning, a hybrid approach common in industry. It uses a small amount of labeled data to guide the learning process for a much larger pool of unlabeled data. This is a critical business tool because manually labeling thousands of data points is often too expensive or time-consuming for practical application. In case study, the practical application of these learning styles spans every major industry, transforming raw data into actionable business intelligence. In banking and finance, supervised learning is used to predict loan defaults. By looking at historical data where customers are already labeled as defaulted or paid, the model can assess the risk of a new applicant. Meanwhile, unsupervised learning allows banks to group customers into segments like high net worth or students without manual tagging, enabling highly targeted marketing. In healthcare, a supervised model can be trained on X-rays labeled by expert radiologists to classify new images as cancerous or benign. Unsupervised learning in medicine, however, is used for discovery, finding unknown patient subgroups that might respond differently to a specific drug, which can lead to breakthroughs in personalized medicine. In manufacturing, supervised models provide predictive maintenance by forecasting if a machine part will fail in a set time frame, while unsupervised models act as anomaly detectors, flagging weird behavior that deviates from the established normal patterns of factory floor operation. The power of combining these methods is best exemplified by Amazon's recommendation engine, which generates 35% of the company's total revenue. The process begins with unsupervised learning, where the AI uses clustering to group 300 million customers by behavior. The AI might discover a group characterized as young males who buy electronics on weekends, without a human ever defining that category. Once these clusters are identified, Amazon applies supervised learning within those groups. The system analyzes the labeled history of what customers in Group A bought, and then uses that data to predict what a specific individual in that group is likely to purchase next. This two-step process, discovering the structure of the customer base and then predicting behavior based on that structure, is why the recommendations feel so personalized. It demonstrates that the most effective AI systems often don't choose between supervised and unsupervised methods, but rather chain them together to turn massive unlabeled datasets into high-precision predictive tools. To implement these concepts, we utilize the scikit-learn library in Python. The provided code snippet demonstrates the side-by-side execution of both learning styles. In Part 1, the script handles supervised learning using a logistic regression model. It generates a synthetic dataset using the function makeClassification. This function is configured with n samples equal to 200, meaning it creates 200 data points, and n features equal to 2, representing variables like age and spending. Crucially, it produces Y labels, which is the answer key containing zeros and ones. In a business context, these represent will not churn and will churn. The command supervisedModel.fit x supervised Y labels is where the learning happens. The model identifies the mathematical relationship between the features and the labels. When we pass a new customer with an age of 35 and a spending score of 2.5 into supervisedModel.predict, the AI uses its learned logic to return a specific classification. Part 2 of the code transitions to unsupervised learning using the k-means algorithm. Here, the data is generated using makeBlobs, which creates natural clusters. Note the line x unsupervised underscore equals makeBlobs. The underscore indicates that we are intentionally discarding the labels because in a real unsupervised scenario, we wouldn't have them. The model is initialized with n clusters equals 3, instructing the AI to find 3 distinct groups. When we call unsupervisedModel.fit x unsupervised, we only provide the data, not the answers. The model calculates the distance between data points and groups them based on proximity. The output, cluster assignments, shows that the AI has invented its own labels to categorize the customers. This code highlights the fundamental technical difference. In supervised learning, the fit function maps inputs to known outputs, whereas in unsupervised learning, fit identifies the underlying distribution and density of the input data itself.
The final stage of the technical workflow is visualization, which confirms the model's performance. The code uses matplotlib to create 2 side-by-side plots. In the supervised learning plot on the left, the data points are colored according to their known labels. You can see a clear division where the model has learned to distinguish between the 2 classes. In the unsupervised learning plot on the right, the points are colored based on the discovered groups the AI found on its own. A critical element here is the cluster centers, marked with the red X. These represent the mathematical average of each group. By identifying these centers, a business can define the typical profile for each customer segment. This leads us to the practical challenge of the HR segmentation problem. As an HR analyst, you would use these exact techniques to take employee data, years of experience, and salary, and apply k-means clustering to find 4 segments. By plotting these, you might find a cluster in the top right corner representing senior high pay and another in the bottom left representing junior low pay. To solidify this understanding, consider the practice questions. When a hospital wants to predict diabetes risk using 50,000 records that already include yes or no outcomes, it is a supervised learning task because the answer is present in the historical data. However, if a logistics company has 1 million GPS records but no labels of good or bad routes, they must use unsupervised learning, specifically clustering, to find patterns of efficiency. The biggest hurdle in supervised learning that semi-supervised learning addresses is the high cost of data labeling. For example, in medical imaging or legal document review, paying experts to label thousands of images or contracts is prohibitively expensive. By understanding these distinctions, you can now look at any business problem and determine the correct path. You have moved from seeing AI as a black box to understanding it as a strategic choice between predicting known outcomes and discovering unknown patterns. You are now equipped to choose the right model, implement the basic training logic in Python, and interpret the resulting data clusters for real-world decision-making.